next example I'd like to do with partial fractions is to look at a denominator where I have repeated factors in that process. So here I want to decompose the fraction x squared minus 2x minus 3 over x minus 1 cubed into partial fractions. Now remember, when we first start out, we want to compare the numerator's power with the denominator power. If the numerator power is the same or bigger than the denominator, we need to do the division to write the quotient plus and then do partial fractions on the remainder over the divisor portion of it. Now here, my highest power in my numerator is square. And just visualizing, don't actually do it, but just visualizing, if you were to multiply out x minus 1 cubed, so you'd have x minus 1 times x minus 1 times x minus 1, by doing all of the process of it, your highest power you would get there is x to the third. So I have it where my numerator's degree is smaller than my denominator's degree, so I don't need to do the division to start it. The thing that I then look at is the denominator factored? Well, yes, it's factored, and its factorization is x minus 1 quantity to the third power. Now the next thing is I would set up the different fractions with my placeholder numerators to get ready to do the work to be able to find our decomposition of this fraction into its partial fractions. But I have to think that if I got a common denominator of x minus 1 cubed, I could have had separate fractions where one of the denominators was just x minus 1, because certainly that would be consumed within that denominator of x minus 1 cubed. I could have had a denominator that was x minus 1 squared. Same thing. So when you have a higher power on a factor, you have a repeated factor in that lowest common denominator, when you set it up, you have to have that factor to each of the powers building up to whatever the highest power is that it occurred within that repeated factorization. Now, what are the numerators going to look like? Well, inside the quantity that's to a power, if inside the quantity that's to a power, it's just the first power, you just have to put that constant placeholder in each spot. So just A, or just B, or just C. If what is in here with the quantity to a power is quadratic, that didn't factor any further, that's when their numerators would have to be the x to the first term and then the constant term. So here I'm going to have a numerator of A, a numerator of B, and a numerator of C. That's the setup. Now the setup is just the thing that you have to worry about from these different situations. The process we do after that is the same throughout, no matter what your denominator's factorization was. So my lowest common denominator is x minus 1 to the third. Remember that from this original startup of the problem. I look at what I need to build each fraction by to get that common denominator. That's what you want to think about. So for my first fraction, it already has an x minus 1 to the first. I need to build it by x minus 1 quantity squared, because to the first power and then squared is how you'd have the x minus 1 to the third for your common denominator. So my first fraction is going to be built top and bottom by x minus 1 squared. And that would give me the x minus 1 to the third common denominator. Plus, the second fraction already has x minus 1 squared. My common denominator is x minus 1 cubed, so it just needs one more factor of x minus 1. So I'm going to build this top and bottom by x minus 1. The third fraction already has the x minus 1 to the third like it's supposed to, so I'm not building that with anything. Now remember what we did from here. Once we built to get our common denominators, then the next thing we did is we multiplied out the numerators and kept the common denominator. Now remember your order of operations. I have to multiply out the x minus 1 quantity squared before I distribute the a through. So remember that when I multiply out x minus 1 quantity squared, that is x squared minus 2x plus 1. So you have to say, go x minus 1 times x minus 1 and go x squared, and we can write this off to the side. So remember that's x minus 1 times x minus 1, which is x squared minus x minus x. Negative 1 times negative 1 is plus 1. So x squared minus 2x plus 1. Okay, and then in the next numerator, I don't have a power on the x minus 1, so I'll just distribute the b. So that's bx minus b all over x minus 1 squared times x minus 1 plus, and then c over x minus 1 cubed. Okay, so we're going to distribute the a through. So I have ax squared minus 2ax plus a plus bx minus b plus c all over, and each of these, if you were to write it as keep the base, add the exponents, is your x minus 1 cubed. So then putting together next to each other the terms that have the same degree on the power of x, and then factoring that out the back, I have ax squared, and there's no other x squared term here, and then I have a minus 2ax and a plus bx. So we would put those next to each other and factor out the x, and then we have a plus a minus b plus c. Now we've done a couple of examples with these, so I'm just going to go ahead and talk us through it and write up our system of equations with a's, b's, and c's that we need to solve to decompose this. All right, so x squared, the only term here has a coefficient of a, so a has to match the coefficient of the x squared in the original problem. There's no coefficient showing, so that's a coefficient of 1. So a has to be 1. Now the terms with the x's are the minus 2a and the plus b. So negative 2a plus b has to match the x coefficient in the original question. So negative 2a plus b has to equal negative 2. And then the ones without the factor of x, a, then minus b plus c, has to equal my constant negative 3. So that's your system that you need to solve. Now this one is going to work really easy with substitution, because I actually have one of the equations that's already got just one letter in it. So I know right off the bat, a has to be 1. So if a is 1, and then when I look and it's like, oh my gosh, this is so fortunate, I even have an equation that has a with just one other letter. So I can go ahead and substitute 1 in for the a. Negative 2 times 1 is negative 2. Add the 2 over, and I get b is equal to 0. So we'll write that out. A is 1. So negative 2 times 1 plus b is equal to negative 2. So that's negative 2 plus b is equal to negative 2. B has to equal 0. And then once we have b is equal to 0 and a is equal to 1, I can come to this third equation, plug in the values for the variables I already know. So I have 1 minus 0 plus c is equal to negative 3. Subtract the 1 over, I get c is equal to negative 4. So now I can just put those in the numerators of the original setup of the problem. So I have 1 over x minus 1. B turned out to be 0, so I won't have that term. And then plus c over x minus 1 cubed. Well, my c is negative 4, so I'm going to bring that minus in front. So minus of 4 over x minus 1 cubed. And so that is our decomposition of that original fraction. For my last example of partial fractions, decomposing a fraction into the individual fractions with lower degree denominators that would be added or subtracted to create that fraction, we're going to do one that needs to have the division process done in the start. So here I have decomposed 2x to the third plus 6x squared plus 3x plus 2 over x cubed plus x squared. Now notice that the numerator's highest power is 3 and the denominator's highest power is 3. So I actually need to do the division to get it where I have a smaller power divided by a higher power to do my partial fractions. So we'll go ahead and set up our x cubed plus x squared as our divisor, and we're dividing that into 2x cubed plus 6x squared plus 3x plus 2. Now to do the division, remember you make sure that it's in descending order, both in the dividend and the divisor, and you just look at the first two terms to see what to do. So what do you multiply x cubed by to get 2x cubed? Or you can think, what is the first term divided by the first term? Well, 2x cubed divided by x cubed is just 2. So I'm going to put 2 up in my quotient, and then I multiply that 2 times the divisor. So 2 times x cubed is 2x cubed, and 2 times x squared is 2x squared. And then as a part of the division, we subtract that portion from our dividend. And when we're subtracting, we have to subtract the entire polynomial. So we need to actually change the signs and then combine. So that'll be minus and a minus. And that's just normally how you do division. Remember, with long division, you would figure out what multiplied to your divisor would get close to without going over into your dividend. And then once you figured it out, you multiply them together and subtract off, because that part of the grouping you've taken care of. So 2x cubed combined with a negative 2x cubed, they cancel. And 6x squared combined with a negative 2x squared is 4x squared. And then bring down the 3x and the 2. And now I look, the highest power in what I'm working on that's still left to be done with the division is 2. The highest power of what I'm dividing by is 3. So the division is done. The quotient is 2 plus the remainder is 4x squared plus 3x plus 2 over the divisor is x cubed plus x squared. So that's my quotient plus remainder over divisor. But this remainder over divisor is a fraction that I can decompose into separate fractions added or subtracted that have a lower degree. So I'm going to keep bringing that 2 plus, but we are actually going to look at doing the partial fractions of that remainder over divisor part of it. So we're pretending like this is the beginning of the problems like we've already seen examples of. Just when we write it at the very end, we want to make sure we include the quotient plus then our partial fractions. All right, so we're going to focus on this to start with. We're going to factor the denominator, and x cubed plus x squared, well, there's a common factor of x squared in there. So we're going to factor out the x squared. So once we factor out the x squared, we have x squared times x plus 1. Now this x squared is like a repeated factor of x. So I have an x to the first and then an x squared. So I'll have in that part of it an x. I could have a denominator of x squared. I could have a denominator of x plus 1. My numerator placeholders are a, b, and c. I don't need a bx plus c right up here because this power on the x came from running up a linear factor to a higher power. Now we're going to build and get common denominators. This first fraction has a denominator of x. The lowest common denominator is x squared times x plus 1. So it needs one more factor of x and a factor of x plus 1. The next denominator has the x squared factor. It needs the x plus 1 factor. The last denominator has the x plus 1. It needs to be built by the factor of x squared. Now remember what we do next? We multiply out the numerators but keep the denominator factored. So we are going to have our common denominator of x squared times x plus 1. And we're going to get, well, ax multiplied to x is ax squared. Then ax times 1 is plus ax. Then plus b times x is plus bx. And then plus b times 1 is b. And then we have plus cx squared. Okay, then remember from here, we find the like terms with the same power on the x and factor that power of the x out in front. So a plus c would be multiplied to x squared. And this is where our partial fraction is that we're working on. What we want to break apart is partial fractions. So a plus c in front of the x squared has to be the same as the number in front of the x squared here. A plus c has to equal 4. Then ax plus bx are the terms with just x to the first. So a plus b has to equal 3. And then the term without a factor of x at all is my term here that's b. So b has to equal 2. So when you're working with one like this, you'll want to make sure that you kind of give some more space and don't cramp it up as much as I needed to just because of the board space. But make sure that you keep the starting problem a little bit further away from what you're currently working on so that you don't equate the wrong values. All right, so here's my system I want to solve. I have the situation where while I could solve this by elimination by addition, by substitution, by Gauss-Jordan elimination, by matrix inverse method, by Cramer's rule, I've got all those options. This worked out where I already know one of the values. B is equal to 2. And so I can back substitute this really quickly to get my other values. If B is equal to 2, and then I look, here is an equation with B in it that only has one other value. So A plus 2 will be equal to 3. Subtract the 2, A is equal to 1. And then now that I have A's value, I can go to the first equation where I have A plus C is equal to 4 and say, well, 1 plus C has to equal 4, so subtract 1C is equal to 3. And so my final work with decomposing that into partial fractions, don't forget your quotient of 2, is 2, then plus, remember how you set it up, A was over just the factor x, so I have 1 over x, plus B was over just the factor x squared, so I have 2 over x squared, and then plus 3 was the placeholder over the factor x plus 1. So plus 3 over x plus 1. And that is your overall decomposition into partial fractions of your original rational expression.